So our next speaker is the global head of the financial services business unit, and his responsibility is business development, but he has a PhD in device physics. So you know where you're at in the technology when you need PhD in device physics to sell the stuff. His name is Andy Steinbach, and he's with NVIDIA, and he's going to tell you, he's here to talk to you about AI, but he's got a long history in device physics at several different semiconductor companies. He's helped start up machine learning practices in other companies, but please join me in welcoming Andy Steinbach of NVIDIA.
Can everybody hear me? Thank you for the very kind introduction, Frank. Well, it's great to be here, being a device physicist, in fact. It's a special point of pride, and I want to talk today about artificial intelligence and deep learning specifically, talk about some of the diverse applications, and then talk at the end about the compute implications. So this is no small task, because deep learning and artificial intelligence, the recent explosion, it's not being compared with decade-level secular trends like it's the new mobile, or it's the new internet, or it's the new PC. It's being compared with no less than being the fourth industrial revolution. So artificial intelligence is being compared with the rise of electronics, the rise of electricity and the rise of the steam engine, and I guess you could go back to the Bronze Age. But so this is a bold claim, and it's fair to ask, is this hype? Is it hyperbole? Well, the proof is in the pudding, so I'll let you answer it for yourself, but I hope to convince you that it is. And please note that these trends, again, they're not decade-level trends. They're 50-year trends, 100-year trends. And what's interesting is I claim that we're probably something like 50 years into the artificial intelligence trend already. So it's quietly been happening as we've been building up our compute power and compute architectures, but most importantly, 50 years of hard work since the 1950s, 1960s, 1970s on algorithms, both machine learning and something called neural networks, deep neural networks. And so finally, what's happened in the last 5 years is it's exploded because basically, in particular, deep neural networks finally worked. And they worked in a spectacular way. And so 2012 was sort of the magic year, what we call the Big Bang at NVIDIA. And what happened in 2012 was that algorithms trained using very large data started to work. I'll talk about that in the next slide. But there was a massive burst of research. There was a whole development of special frameworks, almost like compilers, just to be able to more easily do quick research in deep neural networks. Early adopters like Google's and startups exploded. That's an old number. There's probably 50 billion or more in funding now. And finally, Fortune 500 companies are adopting it. So you ignore this trend at your peril. And what happened was that deep neural networks are particularly good at solving problems with unstructured data. And researchers started smashing all the records and all the benchmarks in artificial intelligence that had been built up and sort of asymptoted, if you know what I mean, for 20, 30, 40 years. So the big thing that happened in 2012 in the upper left was at the annual computer vision benchmark contest, a deep neural network trained with GPUs on very large image data smashed all the machine learning records. It jumped up, that discontinuous jump with the green line you see there, 10 percentage points, and it kept rocketing up until it achieved better than human performance. The same thing happened within the last 3 or 4 years in speech recognition. Speech recognition, handcrafted machine learning algorithms have a 30, 40-year history. And as soon as deep neural networks popped up, research, for example, at Microsoft and other places like Google and Baidu, immediately lower is better on this graph in the upper right, very quickly beat the existing and incumbent records and models. Things that were very difficult to do, like robotics, without being hand-coded for specific tasks, having human-like dexterity. These are robots that were trained at Google. just like a child learns. The camera in the upper part of the image is just watching if it drops it, and then it tries it a different way, and it worked. And then finally, in 2015, just not even 2 years ago, a crowning glory, which is that Google programmed a deep neural network using something called deep reinforcement learning, so powerful that it beat, in the game of strategy called Go, it beat the world's grandmaster, top-rated Go player. This was in 2015, and it's a much more difficult game than chess. You can't just compute the combinations. It's a game of strategy and intuition. This isn't just doing something like learning to walk or learning to speak or learning to say that's a cat and that's a dog, like a 3-year-old would. This is taking, ostensibly, the world's hardest game of strategy, and a machine algorithm beat the world's best human player. That's incredible. So there'll be more as we go through this, but hopefully we're on the road to understanding and getting convinced why it's so revolutionary. Well, at NVIDIA, we make parallel processors. I'll explain a little bit later, but we have, to seize on this opportunity, an autonomous car driving division. And I want to show 2 videos to make artificial intelligence, deep learning in particular, a little bit more personal so that you can sort of touch it. And the first thing that we did when we started our autonomous car driving division is you say, well, maybe I shouldn't try to make a car drive itself like a person right off the bat. So I'll use these image recognition techniques and allow an SDK, a software developer kit, with the hardware so the car manufacturers can make autopilots. If you're texting and you don't see car stopped in front of you, it'll brake. It'll brake if you miss something. It won't let you change lanes if there's a car in your blind spot. Well, what would you need to do that? This is a deep neural network trained to operate and detect images at 60 frames a second. It can detect cars, it can detect pedestrians, stop signs. It has to do it in all kinds of weather. It can semantically segment the image and determine the objects. The purple is drivable surface. With that, it can draw boxes around cars. It knows what cars and vehicles are around it. It can segment lanes. It can use that and check the blind spot to change lanes, for example. And it can categorize the drivable surface there in the middle. The white lines are off the road. The yellow lines are things that you really shouldn't hit. And the red lines are things that you really, really shouldn't hit. It's the Palo Alto Stanford Mall, by the way. It's funny. And you can put all that together, and that's fantastic. This all happened in the last 5 years. 2012 was 0 hour. It's amazing. But what you would have to do with that is you'd probably wrap it, most of us are engineers, in some if-then-else code saying, well, if the sensors tell you there's a car and the velocity unit, you should be stopping, but you're not, stop the car. If you try to change lanes, don't let them if there's someone in their blind spot. But the next phase is much harder. It's how would you make an autonomous driving car? And what you do is you make the algorithm behave or mimic an ensemble of good drivers. I emphasize an ensemble of good drivers, not an average driver, which today, with all our distractedness, would be pretty bad. That's the whole point that we're trying to do. And so what's fascinating is that the car, and this is an NVIDIA test autonomous driving car using our hardware software developer kit, it learns like your son or daughter would at 16. It starts in a parking lot, and it's pretty bad. And it gets confident in the parking lot, and mom or dad says, well, or the driving instructor, let's go out on the road. Sort of halting at first, nervous, not confident, but pretty soon you're navigating with confidence challenges as you learn from more examples. And pretty soon, the autonomous driving car is able to navigate things we never taught it. We never trained this car to navigate a construction roadblock diversion. We never said you can go off the road. We didn't say if off-road, then else, if the angle is this and the grass is smushy. It did it on its own. So in the algorithm world, that ability to generalize, called generalization, to solve new problems that you've never seen, that is the hallmark of intelligence. This is really rather remarkable, and obviously the industry has to regulate and make sure that it's safe, but it's pretty interesting. Now, let's shift gears for a second, and most of us are engineers or scientists here. We probably started at least as some form of a nerd or a geek. I still am proudly so. One of the things that's interesting is some of you may know a lot about this, but I always like to have a mental model or a paradigm for how something kind of fits together. And you're going to see examples that I show where some are things that humans do, like driving a car or robotics. Some things are things that humans do terribly, like assessing 100 million different loans and predicting which one is going to default. That's more like that's predictive analytics. Is there a way that we can think about this that kind of puts it all in one nice bucket? And there is. I'm grossly oversimplifying, but hey, artificial intelligence, it's really just fitting functions. So there's some data. We're going to make an algorithm that looks for a pattern and tries to fit a function to it. I bet you can see a pattern. You're right. There it is. And so there's an input x, and we're trying to fit a function y equals f of x to this data, which fits it the best by some thing, some kind of a metric. And you can think of this as a cause and an effect. Aha, it's getting interesting. An example or an outcome, again, input or output. And so you're telling me, hey, Andy, why are you telling me about, 6th, 7th, 8th grade algebra? Well, what if x wasn't just a single dimension? What if it were millions of dimensions? Every single piece of data in your data lake and your siloed structured databases or data warehouses, what if you were mixing structured and unstructured data? And what if y was your most important business challenge? Like, what is the chance this loan will default? Is this credit card fraud? Does this patient have cancer? Is this jet engine okay for the next flight, or does it need maintenance early? Well, it's really getting interesting now. And so what you can think of this as a function, but it's fitting very complicated nonlinear functions in an incredibly huge number of dimensions. And that's what machine learning historically has done pretty well for maybe the last few decades. What deep learning does is it can deal with nonlinear interactions and functions much better than ordinary machine learning, which tends to be things like linear regression. I'm not doing it service, they're more advanced algorithms. But this is incredibly complicated function fitting, and that's why it can generalize so well and not overfit, because when you have complicated models, overfitting is a big problem. And so I think of this as a question or answer pair. You're sifting through all the data in your data lake or database or in the real world, and you're trying to synthesize an answer. And so the standard way of doing artificial intelligence that's mostly what's in use today in production is called supervised learning. You have many, many examples of the behavior you want to synthesize, like the people driving, or that these are images, and this is a cat and this is a dog. That's called supervised learning. You have labels or a target that you're trying to emulate, like driving the car for hopefully a good driver. Well, you can see that if you can do this, as I'm showing, it's really profound. It's a revolution in the scientific method, because what's science, at the risk of condescending to the entire room, because we're all scientists, or most of us, and engineers. Scientific theory is, at least is the way I see it, right? You guess a model. Some people guessed a differential equation or a model, and then they kind of prove, that's that middle box, they validate it by fitting data, and maybe they tune a few parameters, but after a lot of trial and error, they stamp that theory as it works in this regime, and then you can predict things, and that's electrical engineering and mechanical engineering and physics and chemistry, and you get into softer sciences where suddenly you can't do that, but it works incredibly well. We have these chips with billions of transistors, and it's amazing, but we don't have that for predicting credit card fraud or driving a car or understanding if some packets are a cyber attack when they're coming into your network, because there's no laws of physics of a cyber attack or credit card fraud. There's only patterns of past behavior. And so AI turns this around, but it's a new kind of a scientific method data science, it doesn't start with the model, guess the right model, and then validate it. It starts with the data first. So the data in our data lakes, the data in our databases, the data in our fabs, in our whatever, and it takes that data and it builds a model around it that fits it. And the revolution in deep learning is it can build incredibly complicated models and incredibly accurate models. You fit the parameters, there's a big risk of overfitting, but there are ways to avoid that. And then you have a prediction. So you have this thing can predict things we never predicted before. It's like electrical engineering or physics, or sorry, I'm biased in my sciences, but for all these other things that we could never really have a good theory of. And you can get 90% accuracy, 99% accuracy. And so contrast that, this is predictive analytics, contrast that with data analytics. No offense, because a lot of us do data analytics and spend a lot of time, but it takes historical data, for example, in our data lakes, and it typically does backward-looking analysis, queries, averaging, and you get insights into what happened, past tense. AI gives you predictions into the future, what will happen next. And that's a profound difference. And the two are complementary, by the way, because we've spent the last 10 or 20 years collecting all this data, doing some stuff with it, and wondering when we're ever going to finally monetize our Hadoop data lake, for example. And finally we can, because we can sift through it with AI algorithms and answer our most challenging business questions. So I'll go through this slide quickly because I'm probably running a little slow, but it's really a new paradigm for big data. Some of you, many of you will recognize on the top there a little cartoon of a data analytics. It's a typical data lake environment. This is a Lambda architecture where some streaming data comes in. It's stored in some kind of data warehouse or Hadoop infrastructure. You might have a batch data analytics jobs that calculate the closing of your quarter, or all kinds of statistical reports and data analytics reports, business intelligence reports. You may have a speed layer like Spark or something proprietary that lets you serve up applications that query the most recent events that have happened that the batch job might miss out on, and you answer all kinds of business questions. But artificial intelligence is this sort of virtuous cycle where you take that big data, you in this circle on the bottom, you build a powerful model, you deploy that model, and then as new data streams in at the edge, you keep learning, and it just gets better and better. And every one of those models is like a little laws of physics or Navier-Stokes equation for mechanical engineering for your problem, for credit card fraud, for what is the probability, what will your speed bins be for this high-K metal gate transistor with this lot of wafers going through halfway through the run card, things like that. It's really remarkable. And so the interesting thing with this model is now you have these little artificial brains, these little artificial intelligences, and you can push the intelligence out to the edge of the network. It doesn't have to be in your data center. It's in your car, it's in an airplane, it's on an oil rig in the North Pacific where you'd rather not have any people, or a mine in Africa because it's a dangerous environment. And wouldn't it be great if you don't have to risk people's lives to be there? So pushing that intelligence out to the edge, and even taking data in at the edge, learning incrementally at the edge and sending that incremental learning back to the data center to update your models. Well, let's shift gears again. Let's talk a little bit about why these networks are so special. So I guess I'll go through this quickly because it's easy to get in the weeds, but with machine learning, the name of the game for the last 10, 20 years, 30 years is you handcraft features. A lot of us were familiar with Fourier transforms. So you have a complicated time domain signal, you take a Fourier transform, and out pops two frequencies. And you say, oh, that's easy. I can get rid of the noise with a high-pass filter or low-pass filter. You transformed to a domain where the signal looked a very simple way. So handcrafted feature engineering is that process of finding that Fourier transform, or that whatever it is that transforms you into a space where your data makes sense, and then you kind of just separate it with lines between it. That's the learning process. The learning, some machine learning enthusiasts will not like me for this, but it's relatively simple. And that's absolutely not fair. and machine learning stands on a pedestal of 50 years of magnificent Bayesian probability theory, and the frameworks between deep learning and machine learning are more similar than they are different. But the one thing that machine learning doesn't do well is you need to apply a lot of domain expertise to make these handcrafted features. Well, one of the big things with deep learning is that it uses incredibly complicated models with many more parameters to find the features themselves. So this is a network trained on faces. And whenever you train a convolutional neural image network, that's what this is, on any objects, the first layer in this network, this cartoon, these are weights and biases, and some of you may have seen this. If I get into explaining it, it'll go too much into the weeds. But you're basically training the network, you're training the numerical weights of these sets of connections, and the first layer of images are these filters to the right of the woman's face. Those are called Gabor filters. They're line and edge filters, and it makes the observation that you can construct hierarchically any feature that you can draw with these simple basis functions. So for faces, you take these lines and edges, you construct parts of a face and then an entire face. And these are hierarchical feature sets. A lot of problems in the world are hierarchical. Language, right? Characters, words, sentences, paragraphs, novels, Shakespeare. The human body, medicine, atoms, proteins, molecules, subcellular structure, cellular structure, organs, functioning organism. Again and again, plenty of problems like that. And so what deep learning can do is it can automatically, given enough data, find these ways to factorize and find features that you would not have discovered because there are just too many combinations by yourself. And so the traditional machine learning approach would take an image of a cat and basically say, well, let me construct an ear detector, and a cat has triangular ears and a round head and a chubby body. So let me make a chubby body detector. Well, a deep neural network would just take this first layer and say, well, here's my ear detector. It's two 45-degree lines and a flat line, and that looks like a cat's ear if I scale it right. And there's some other attributes like color or texture, that it's fuzzy. And so you can build a cat that way. And so you can solve for things that you never would have solved for. The other thing deep neural networks can do better than machine learning, again, I'm taking a little bit poetic license here, is they can solve highly nonlinear problems. This is actually a fairly simple neural network problem, but Google wanted to try to minimize the power that they use in their huge data center with all their servers. You can imagine, it's massive. And so this is a curve, the red, of the actual power usage efficiency. So it's the difference between the power that you actually need to run the equipment that's dissipated and the power at the trunk line. And when it says 1.1, that means 10% was wasted. And it fluctuates as the servers go on and off, as the temperature of the chillers makes your data center different airflows and different temperatures. And they have thousands of sensors that give the state of the air, the chillers, the temperature, the air circulation, the workloads on all the different servers and their types and their configuration, literally, whether they're running Unix or some other operating system. And the curve you get is incredibly complicated, but guess what? If you take sort of 1,000 variables, let's say, and you feed in the power usage efficiency that you actually had, so this is a supervised case because you have examples of the answer, and you do that with several years of data, and of course, ideally your configuration of servers should stay the same, you can predict that behavior. So now I feed in the current value of my variables, or what I might like it to be, and it can predict the power usage efficiency. Look at that nonlinear curve. It looks like a Forex trading currency stock chart or something, but it can predict it. And that's remarkable. So the ability to map incredibly complicated nonlinear behavior is a big thing. And just to geek out for one more slide, and then I'll transition into some applications. The thing that's so amazing about deep neural networks, and the reason that some of the pioneers in the field for 20, 30, 40 years sort of never gave up, is they knew that there was something special, which is that if this is a neural network and you input an image Think about this. How many images are there in a megapixel image with just a 256 grayscale? There are 256 to the millionth power unique individual images. There's 10 to the 78 atoms in the universe, 256 to the millionth power. And somehow, when I write an image detection algorithm that says that's a cat or that's a pedestrian, I have to take an input that could be any of those 256 to the millionth power images and find a way to sift through it and find a tiny infinitesimal subset in that space of images that I would say those look like cats or those look like dogs or pedestrians. And guess what? One of the magic of deep neural networks is whenever you have an algorithm or a function with a lot of inputs, or you're trying to solve a differential equation in space with a lot of inputs, a complicated integrated circuit, there's an explosion in complexity that happens with the number of variables. And in machine learning, it's on page 7 of every machine learning book. It's called the curse of dimensionality. And it means that as you increase the number of variables n, the number of states you have to sift through explodes exponentially, goes to e to the nth power or something like that. Well, guess what? If as I step through this network, I rule out, say I'm trying to identify cat, that some of these things are cats, some are dogs. If I eliminate only a factor of 2 of the states at every point, but every time I step through the network, I eliminate 2 more. Guess what? That's a decaying exponential that's like an e to the minus n. So it's searching through this space with exponential complexity and efficiency to find that one or small number of right answers. And the only trick is this is in prediction mode. Can you train it? So how do you train these networks? Some of them have millions or even billions of parameters. And so the number of combinations is even bigger than that crazy number I just gave you a minute ago. And so it turns out, and one of the magics of deep neural network is it's an optimization problem. You tell it what the answer is, and it adjusts all these millions of parameters to get closer to the right answer. And then it's just an iterative process of getting a wrong answer, correcting all the weights with a lot of computing power, and it's an optimization problem. So see that minimum, that dish-shaped thing there in the upper right. The point at the bottom, the minimum, is the answer. If it makes you feel better, you could flip it around and pretend that we're climbing Mount Everest. But it's an optimization problem where you're trying to find the minimum or the maximum. And so, it looks simple, right? This is a minimization algorithm. It's called backpropagation. By the way, it was invented in 1987 in a famous paper. But it takes massive compute, and luckily it's amenable to parallel compute. And so how do we do all these amazing applications like computer vision, speech recognition, natural language processing, we'll talk about in a second? Do we code these algorithms? Do we say, if I see this, then do that? No. It's no if then else rule-based programming. We take a network and we feed it a bunch of data, and we do this optimization thing where we optimize the weights, and at the end, if it converges to an accuracy we're happy with, we say we're done, and we can use it. And so there have been a set of developments since that magic year of 2012 where deep learning frameworks were constructed by a lot of companies, and luckily for all of us, they're all open source. So it's really an open source kind of an ethos or philosophy, and TensorFlow, MXNet, Caffe, Torch, Tiano, I'm sure you've heard of some of them. And so what they do is they very efficiently let you construct these networks and train them. And you can train them on different types of compute power, but what you'll find is that if you have very much data at all, you want to use parallel computing. Otherwise, it'll take an unreasonable amount of time, and that's where GPUs come in. I'll talk about that at the end. I am badly in need of speeding up. So very quickly, you realize that it goes beyond just a one-trick pony. It's not just speech. It's not just computer vision. Using these frameworks, you can plug a vision network into a language network, and you can say, be great, not just to say that that lower right image on the left is a cat, but it's a black cat sitting on top of a suitcase. Well, guess what? They took a trained image network that could say that's a cat, that's a suitcase. They put human annotated or labeled images and they trained it, and the computer generated those annotations. And I don't think you can tell the difference from a human. Now, here's the other beauty of it, is that these frameworks allow cross-pollination of different verticals. So someone in medical research, and a lot of these things are research. So this paper on the left was from Stanford. A lot of them will post their code on GitHub, open source. You can take that code in these deep learning frameworks. A medical researcher took that and said, if you can do that, I'll bet I can replicate or imitate the diagnosis the pathologist or radiologist would have given of these chest x-rays screening for lung cancer, and it worked. And so these frameworks allow you to take an example that's very close to what you want to do, but often in another domain, and very quickly get something that's working, at least for research. Getting it to production, of course, is a whole other challenge. I'm going to speed up, but it's really revolutionizing medicine. This was actually a fairly simple paper from a while ago, but you can show that sometimes patients come into an emergency room and they look fine and then they crash, and no one can figure out what's wrong with them. It turns out that by just putting in the half a dozen basic things like pulse ox, the way that they would monitor you in an emergency room, you can predict the probability of them crashing and dying. And if you can do that and you can get warning, you can figure out, what to do and what the problem is. It's not too far of a step from that to say that what if we took a patient's all their medical history, the analytics, their family history, the history of similar patients, and we did this supervised learning where we said, these are the outcomes that these patients have, and this patient looks a lot like these other ones. And so a doctor could get something right there in the office to say to some patient, hey, you've got a 70% chance in the next year of congestive heart failure and a 91% chance in the next 3 years. You better do something about it. And this kind of thing is absolutely revolutionizing medicine. It's really revolutionizing all kinds of industries and domains. I'm doing a lot of work in finance. So this is an example from Stanford where they took 120 million loans from 20 years, something like several billion, I think it was 3.5 billion monthly loan data points. This is what we know about this person with this, it's a mortgage loan. This is whether they defaulted, this is whether they were 1 or 2 or 3 months late. And they trained a network, and they wanted, you want to predict delinquency or prepayment, that you're going to pay it and get a different loan. And so on this graph here is the actual observed number of prepayments versus the predicted number by the model. And the black line, 45 degrees, is ground truth. That's a perfect model. And the blue deep learning model, you can see, is just hugging the ground truth. The red is a more basic machine learning logistic regression, linear regression model. And you can see it's not nearly as accurate. So that is cash money for companies whose core competence is to understand the risk of lending. Insurance companies are all over this, because what is an insurance company? Their cost of goods sold of their product is guessing how much they're going to pay out statistically to their customers. That's their cost of goods sold. So, I mean, that's, we call that underwriting, but it's predictive analytics. So, for example, if you're an insurance company and you want to issue crop insurance, they can take satellite data. Of course, they can say this is their field and this is their crops, but more importantly, they can take historical crop yield, weather patterns, and by using supervised learning with the labeled historical crop yield data, they can do a model that will basically predict how much you would expect to pay out for a given crop insurance. And insurance is very elastic. So if you can hit your target margin, but lower your cost by 10%, and still hit your target margin, you might get 50% more business in a certain segment. So this is absolutely revolutionizing all kinds of industries. I'll go through this one quickly. Quant investment banks and hedge funds are going crazy. They build things called factor models, which try to predict what short and long-term factors will predict the return of a security. And now the whole world is your factor model. You can take external data, open data from the internet, but things that might be hidden. You can do speech detection on earnings calls and get the answer in a second, not the next day. There are companies that are selling proprietary data feeds to map the Earth every 15 minutes at a sub-meter resolution. That means you can track, in principle, the location of every tanker, every ship on the planet. Quandl is doing all kinds of receipts, and so you can predict the behavior that correlates to stock returns of, for example, retail businesses. So that's a huge thing. Semiconductor industry, it's obvious that you can do things like defect detection, again, using image processing. But what if in your fab, you could take the outcome of lots going through your fab, you could say, I know from my electrical test I have failure data, defects, and I have speed bins and parametric data for transistors or for memory. And what if at every step in the run card I could throw in all my information, all my metrology, all my defect inspection, all the sensor data from all my CVD and PVD process tools and all that jazz and my lithography. You could predict at every point in the run card more than you knew before. What's my yield going to be on this lot, on this wafer? Could I do something to correct it parametrically? What kind of speed bins am I going to have in 4 months when this high-speed logic goes through the production line? It's really revolutionizing things like this, and people are gearing up to do these applications. There is another kind of learning where you don't have labels called unsupervised learning. And so here's a video for 40 seconds. This is a bunch of images, but we didn't tell the deep learning algorithm what the images represent. There are no labels, cat or dog. It's clustering images that it thinks somehow are similar. It doesn't understand them, but it says these different clusters are somehow similar, and we're manipulating it in a visualization tool. But so the question is, did it do its job? Did it find things that were similar? Let's look at this cluster. Oh, it's military aircraft. It didn't know that. That's called unsupervised learning. And so you can also do that semantically with language. You can take documents, and it will learn how different words cluster. And without labeling their meaning, it will learn relationships. So you can look into these clusters, just like in that last thing, but this was deep neural network trained on documents, something called an RNN, recurrent neural network. And look, it clustered countries, Switzerland, Mexico, Brazil. It figured out that states in the US were somehow similar. But it can do better than that. It can figure out semantic relationships and meaning. So this blew people away when this happened. I love this. So you can do something called an embedding, and it will embed the words in a lower dimensional vector space. And you can do vector addition on semantic meaning. So the high dimensional vectors that represent king, queen, man, and woman, you can take in a vector sense, just like linear algebra that we all studied. King minus man plus woman equals queen. And this just came out of it. It just learned that on its own. They were blown away when they saw this. And there's so many things like that. Let's see. I am late, so I'm going to skip this example that was on unsupervised learning and shift to the very last few slides of my talk, which is on the implications for compute architecture. And I'm sorry, I see I'm running late. I'll try to go through this super quickly so that we don't push back the next speaker. But big data requires massive compute. Small data now, with customers I work with, is a few terabytes. Oh, you have small data, you've got 5 terabytes. Dozens and hundreds of terabytes going to petabytes, going to whatever. That's the kind of data that we're going to see in the future in our data lakes. And so the challenge is that to train that data on these massive models requires incredibly huge, literally supercompute power. And so the problem is that okay, Moore's law is, as we all know, is rolling over now. But we all know as well that starting back at 65 nanometers, you couldn't crank up the clock speed indefinitely. So the single-threaded performance started rolling over. It's that lower blue curve way before Moore's law started flattening out. So what that implies is that you have to go to a parallel compute architecture. And I had a nice video that I'm going to skip for time, but that shows how an NVIDIA GPU has typically 3,000 to 5,000 parallel cores, and not for every operation, but for numerically intensive operations, Those 5,000 cores are something on the order of 100 times faster than a CPU that might have 10, 20, 50 parallel cores if you have a dual socket machine. And so,
all right, I introduce to you Leonardo, and he's going to paint a picture for you guys in the way that a CPU might do it, as a series of discrete actions performed sequentially, one after the other. Let me speed it up. Ladies and gentlemen,
Leonardo 2.0. 4, 3, 2, 1.
ladies and gentlemen, science class is now over. Thank you.
and what's happening is that, so you have the potential with graphics processing units, which came from the world of video. We've repurposed them to be general computing machines. That's what we do at NVIDIA. And we have a language called CUDA, which allows the deep learning framework programmers to easily leverage these parallel computing cores. And so the good news is that even though Moore's law is shallowing and single-threaded performance already was shallowing, we've still got a lot of juice left to squeeze in this lemon to make some sweet lemonade, because you see that the CPU performance is scaling very weakly. Now, both in compute power and memory bandwidth, the green line is the GPU compute power in flops and memory bandwidth. And so what you need is, typically, if you would have tried to do something like deep learning, machine learning, or complicated data analytics, you would typically scale out to a large cluster, maybe something like a Spark cluster. But nowadays, people that are using these deep neural networks, they don't necessarily want to scale out to a large cluster. They can scale up to a dense GPU node server that might have 8 GPUs in it. And because it doesn't have to talk over the network, it has high-speed interconnects within the same box. You can use those 5,000 cores on every GPU, and they can communicate efficiently. And what you get is quite remarkable. So we built, and I guess this is the sales pitch of this, of this talk, but we built a custom-built supercomputer. It's a 3U server with 8 of our latest GPUs. And this box, called the DGX-1, is equivalent to, it's faster than 128 Knights Landing servers when you benchmark it on an image recognition deep neural and network and other neural network benchmarks. And beyond just raw supercompute power, it has a fully integrated software stack where all of the deep learning frameworks are containerized, and you can download them from software registries. So everything you need as an enterprise to have your data science team be productive. And that one box that's a 3-year server, that's more powerful than the most powerful supercomputer in the world was in 2004. It was something called the Earth Simulator in Tokyo. It had its own building, and it was a $2 billion supercomputer, #1 in the world. This thing is more powerful. It's a 3U server. So it's really remarkable the power that you get, and this is exactly what's needed to train these deep neural networks. I'll just make this the last slide because I do apologize I'm running late. But we asked ourselves, well, if this one box is equal to the most powerful supercomputer in 2004 and 128 state-of-the-art data center servers now, what would happen if you plugged 128 of these boxes together? If you really needed power to crank through deep learning, well, we did it, because we're NVIDIA and we have them, and we plugged them together with high-performance computing fiber optics. Within each box, there are these very high-speed links that are faster, called NVLink, faster than PCIe Express, and you immediately get, I hope I'm not misquoting this, it's the 26th or the 28th most powerful supercomputer in the world on the top 500 list. It was #1 on the Green 500 list, and we're using it for deep learning research. There's a deep learning framework just for cancer that mixes HPC molecular dynamics and deep learning. And by the way, if you only plugged 13 of these DGX together, you'd already get onto the top 500 list. And so we have the power, We have the data in our Hadoop data lakes and our databases, and we have the algorithms. So the next 50 years is going to be about this. And so I hope that was interesting, and thank you very much for your time.
Thank you so much, Andy.